Hey everybody, my name is Anand Kappagantu. Today our team will be presenting on the dual lander Mars Ascent vehicle. Here's our team, that's me, Anand, and we also have David, Varick, and Ricardo presenting with us today. A little bit of background and motivation for this project. NASA is planning to land humans on Mars before the year 2040. Prior to that, some of the steps that need to be completed is to show unmanned demonstrations for feasibility proof, and then getting humans into the Mars orbit, and then getting Mars humans from the orbit to the surface. To complete this mission, we will require what's called a Mars Ascent vehicle in order to bring the astronauts back from Mars to the surface of the Earth. Some of our key stakeholders and needs that we identified, primarily NASA, scientific community, and ESA, and overall their needs lie around generating crew liftoff capabilities from the Mars surface, having a certain minimum payload capacity, ability to return samples from Mars surface back to Earth, and communicating between Mars and Earth in order to maintain survivability. Some of the current designs for similar missions that are available, we have the SpaceX Starship, the Lockheed Martin MADV, and NASA's own MAV. Some of the common themes that you'll notice here is they all have in-space refueling, but one major drawback is that they do not have autonomous surface propellant transfer. For this project, we will be focusing on developing an autonomous system for propellant transfer on the Mars surface. So the way we plan to do this is to take two landers to the surface of Mars that land a certain distance apart from each other. And this would happen 2 years prior to astronauts' arrival on the Mars surface. So we would use that 2-year window to construct a fuel transfer between what we're calling Lander 2, carrying the fuel, and MAV, which will lift off astronauts from the surface. So here's our concept operations. We have Lander 2 approaching to the Mars Ascent vehicle, would take about a 6-month window depending on the distance they land from each other, and then build a connection for propellant transfer, then actually transfer the propellant, perform safety checks, and separate the landers before it goes into dormancy mode, waiting for the astronauts arrive. These phases can be monitored from mission control on Earth. To support our decision, we followed a systems engineering methodology to identify requirements, draft out QFD findings, identify potential solutions, trade-over solutions, and make our final decision. You will see all of these steps covered through the presentation today. Some of our high-level requirements that I would like to touch on are here in our requirement flowdown diagram under mission specifications. The key ones here are our payload capacity needs to be able to carry 2 crew members off of the surface of Mars, and the Lander 2 needs to be able to travel to the Ascent vehicle and transfer fuel, and we would like to keep them both under a combined weight of 25 metric tons. So our functional breakdown to understand the differences between the Ascent vehicle and the lander. Our Ascent vehicle will need to be able to launch off the surface of Mars, carrying 2 astronauts, and then dock with deep space transport. Our Lander 2, on the other hand, it will carry the propellant and transfer the propellant and will not launch off of the surface of Mars. Our functional flow diagram here shows kind of the operations of what will happen through the mission. We have once the 2 landers have landed, Lander 2 will move to the MAV and transfer the propellant. And then upon propellant transfer, the MAV is waiting for the astronauts to arrive. Once the astronauts arrive, it will receive them, provide life support for them through the launch until it is able to dock with deep space transport. And then once the docking is complete, transfer the astronauts to the DST, and the mission would be complete. Now I'm going to pass it off to David to talk about our QFD.
Hi, my name is David Hermanns, and I'll be presenting on our mission and design's quality function deployment, as well as our mission and system level design requirement diagrams. We developed our design in conjunction with the AIAA Landers Team Space Design Competition RFP. The RFP explicitly stated engineering characteristics that translated to Room 2 of the QFD, and other requirements were found in NASA Strategic Analysis 2021, or SAC 21, Human Mars Architecture papers. Many of our functional requirements are not significantly correlated through our QFD, which allows for fewer design trade-offs, but our power supply and power draw are correlated with many other requirements that are especially critical to life support systems. This is also reflected in our QFD's importance rating for our customer requirements. QFD technical competitive assessment, we compared 4 alternatives against our set of requirements and our own design. We compared the SpaceX Starship, the Lockheed Martin MADV, the NASA Unmanned MAV, and the Blue Origin HLS systems. The SpaceX Starship and the Blue Origin HLS systems performed well against life support related requirements, but like other competitors, they were too large and had too large of a power draw as well. None of our competitors performed well either with surface refueling with an autonomous system. Our design performed the best for all requirements when compared to the alternatives on average, never scoring less than a 3, while other requirements scored as low as 1s and 2s. For the QFD customer competitive assessment, we compared the same 4 alternatives against our customer requirements and our own design. Again, the SpaceX Starship performed well because it's over-designed for the current Mars mission profile, and as in the technical comparison, our competitors' designs were too large and too heavy. The NASA unmanned system does not perform well for astronaut and NASA safety requirements either. Our product scored an average of 3.91, higher than any of the other averages from the competitors' designs. This, along with our technical competitive assessment and our technical importance ratings, demonstrates that our system is properly designed for the mission profile, especially when taking into account astronaut safety and human life support systems. For our requirements diagram, we designated our top-level requirement to be the 2-lander mission as a whole. From there, we identified 4 mission-level requirements and allocated all other requirements to either the MAV system or the Lander 2 system. This breakdown of system-level requirements allowed us to meet the customer-defined requirements from the AIAA RFP paper, as well as meet industry standards and external stakeholder requirements for safety and science as well. As previously discussed, this slide shows the system-level requirements breakdown for the MAV system. The MAV system takes on most of the responsibility for the human life support requirements, as well as return of the astronauts and samples from the surface of Mars to the deep space transport. Each of the identified subsystems also carries with it a set of subsystem level requirements, not shown here. For example, under MAV ECLS subsystem, we have the subsystem level requirement. The MAV ECLS subsystem must maintain internal cabin pressure between 18 and 27 degrees Celsius, which is derived from the MAV crew support system requirement for the overall MAV subsystem. Additionally, under MAV structural subsystem, we have the requirement defining that the MAV structural subsystem must have a docking ring such that astronauts and materials can be transferred between the MAV and the DST, which helps meet the requirement DST docking, ID 1.1.13. A similar structure occurs for the requirements diagram for the Lander 2 system. Many of the requirements regarding fuel transfer, power generation, and system movement were levied on the Lander 2 system, as evidenced by requirement 1.2.11 on the right. The Lander 2 subsystem also has subsystem level requirements that help satisfy mission requirements, such as the L2 GNC subsystem requirement that states the L2 GNC subsystem must capture imagery of terrain around the L2 system as a whole for the purpose of route planning, which allows us to move the Lander 2 subsystem.
Thank you, David, for your presentation, and I will continue talking about the Lander 2 subsystems. So the first 4 subsystems that we have here are the avionics, communication, GNC, and thermal. Those subsystems were defined based on previous Mars rovers developed by NASA, and the last 3, the power transportation and propellant transfer. They will be evaluated later considering different technologies. And we have done an initial parametric analysis considering the mass and the power demand of the Lander 2. And using metric draw, we have created a block diagram for the Lander 2. For the avionics subsystems here, for example, we have the command and data handling, the onboard computer, and the storage, data storage. For the communication subsystems, we are assuming that it will have a UHF antenna, transmitter, and receiver components, low rate antenna, and high rate antenna. For the guidance, navigation, and control subsystems, our lander will have navigation cams, infrared sensors, inertial measurement unit, and the lidar. For the power subsystem, we have here only the function because we will talk more about the elements considering different technologies, as I said. So we assume that we have power, storage, generation, and distribution capabilities. And the last subsystems are the transportation, thermal, and the propellant subsystem. So we have identified some possible technologies that we could use to generate power, storage power, for the transportation and the transfer as shown here on this table. We have created 4 possible alternatives of the Lander 2, combining those different technologies. After that, we have implemented a hypothesis technique to make a decision and select the best alternative between those ones. And we have used different criterions such as weight, power storage efficiency, reliability, and transportation capability to identify the best alternative. And to do this, we have used weights for those different criterions, and some of them should be maximized and some of them minimized. After that, the alternative 2 was the best one, and these alternatives use a higher isotope thermoelectric power generation for power generation, or lithium-ion batteries for power storage. To move the Lander 2, we'll use tracks with 4 motors. For the propellant transfer subsystem, we will have a oxidizer and fuel combined in one large tank, but internally the oxidizer and the fuel will be separated. The transfer tube uses an extension arm, and the propellant docking system that will connect the landers will be partially autonomous because before the final connection, the mission control on Earth will do a final check, guarantee that everything will work properly.
All right, thank you, Ricardo. So now that we've looked at the Lander 2 alternatives and made a decision, we are now going to look at the Mars Ascent vehicle alternatives and perform the same process. For the first alternatives, the vehicle has 2 stages and it is fueled with hydrogen and oxygen. Now, both of these have to be stored as a liquid, so the refrigeration systems will require a decent amount of power in order to stay operating. So for this, the fission surface power system is used to provide the necessary energy. For the second alternative, it is again 2 stages, but this time hydrazine is used as the fuel. That means that only liquid oxygen needs to be stored and it only needs to be kept cold for refrigeration, so a much smaller PV cell array system can be used. Hydrogen is a good fuel in this case because it can easily be stored at room temperature, which is around the temperatures that Mars experiences. This design also does not use turbo machinery, and the engines are instead pressure fed, which saves on weight and complexity. For the third alternative, this is a single stage to orbit, and instead of hydrazine, in this case, methane is used. So again, this doesn't need refrigeration, only liquid oxygen does. In this case, the lithium batteries will be pre-charged, and the power for the refrigeration system will be from the lithium-ion batteries until the Lander 2 arrives. At that point, the Mars Ascent vehicle can then attach to the fission surface power system and use the energy from that. Again, methane doesn't need to be refrigerated, and it is very easy to store. So now we are going to evaluate the alternatives. So looking at the criteria, the gross weight is just the total weight of the Mars Ascent vehicle as well as the supporting systems, which in this case are the power systems that we looked at. The power required is all the power necessary for the refrigeration, communications, all the other systems. The stability of the fuel and oxidizer is important as it does have to be transported to Mars and then wait approximately 2 years. So you don't want too much of the fuel or oxidizer to break down. The ease of storage is another consideration, as refrigeration and just storage of liquid hydrogen in general is more difficult than some of the other options. The overall design safety is obviously very important, and it has actually the highest weight of all of the criteria. And finally, system complexity. So that looks at turbo machinery versus the pressure-fed system, as well as 1 and 2 stages and some other smaller factors. So they were evaluated, and you can see that the third alternative actually performed the highest. So this was the closest to the ideal solution, with alternative 2 not far behind, and alternative 1 did not perform well because of all of the weight and complexity of the system. So looking at the final concept, as you can see, we have the Lander 2 design that Ricardo talked about. So that has the radioisotope power system, and it uses tracks with 4 motors. And then the Mars Ascent vehicle is single stage, it uses methane, and there's no power generation. So looking at the features in depth, so the lithium batteries are a good alternative because they're a lot lighter than the power generation systems. Methane is a very stable and easy fuel, and it also has a lot of thrust. For the single stage, this is easier because of the lower Martian gravity, and again, it is less complex than 2 stages, as you need the first stage to separate in order for the launch to be successful. And then looking at the Lander 2, this uses the radioisotope power system. This is consistent to provide power whether it's day or night and whether there's a sandstorm or not. The tracks are the best for the transportation because they are good at carrying heavy loads through the Martian soil. And for the transfer tool, the extension arm was used because this has the ability to adapt to different situations depending on how the rover and the lander will actually be oriented. So now looking at some risk management. So see, these are some of the risks and our strategy to mitigate them. In many space projects, failing to meet cost is a very common issue. And so we are going to have a strict financial management plan, and we will have a very conscious budget tracking and reviews every month to try to remain under the budget. One of the biggest issues will be the fuel transfer, as this has never been done before. So of course, we will have to do very rigorous testing in lots of different conditions and lots of different configurations to ensure that the system is resilient. Looking at some more risk, of course, the thrust failure would be very bad for the astronauts if they cannot leave the surface. This is always a worry with thrust systems, so we will, of course, perform lots of testing and make sure all of the components are as reliable as possible to hopefully ensure the launch will happen and happen successfully. So in conclusion, sending humans to Mars is a very difficult challenge, and there are a lot of technologies that we will currently need to develop in order to meet this challenge. And of course, one of the important aspects of this is bringing humans back from Mars and returning them to Earth. And for this, a Mars Ascent vehicle is necessary. So our Mars dual lander design fulfills all the stakeholder requirements that were set out for us to bring the astronauts back from Mars. And this is designed better than the previously looked at competing designs, and it is better suited to the mission. So it is the better choice to look at than the competitors.